Here is part B for our rotational kinematics and torque problem set. Part A, you can see in a previous video, the answer was 16 rotations. I'll put a link to that previous video. We're going to do part B here, and so now we're going to find the frictional force causing this gyroscope to come to a stop. Now we're given a few things. So we're given the following. We're given the diameter of the gyroscope, and we're also told the gyroscope's a solid disk. So first of all, the radius of the gyroscope is just half the diameter. Oops. There we go. So that's going to be 3 centimeters, or in SI units, we want that in meters, so it's 0.03 meters. We also know the mass of the gyroscope. We're told that it's 100 grams, and we want that in kilograms, so that's 0.100 kilograms. And we know that it's a solid disk. That's important. The moment of inertia for a solid disk is 1/2 times the mass times the radius squared. We can use the information from before, and that is that the angular acceleration is negative 0.700 radians per second squared. Okay, so how are we going to find the frictional torque? So the force of friction is what's causing this to come to a stop. So let's remember our equation for torque. Torque is just equal to the moment of inertia times the angular acceleration. We know, well, we can compute all of this. So moment of inertia is 1/2 mr squared, and our angular acceleration is alpha. We can plug in all of our numbers. We have 1/2 times the mass, which is 0.1 kilograms, times the radius squared, which is 0.03 meters squared, times our angular acceleration, negative 0.700 radians per second squared. Okay, so the straightforward calculation from here, we get negative 0.000315. And if we look at the units here, it's kilograms meters squared over seconds squared. We can drop the radians as it's a fictitious unit. And we know that this is a Newton meter. So we can write the torque as negative 3.15 times 10 to the minus 5 Newton times meters. Okay, so this torque, something to note here, it's negative. So that comes from the force of friction slowing it down. If we go back to our picture, I originally had our disk rotating counterclockwise, so this torque is causing a clockwise torque. So there's a force of friction. We could draw maybe an arrow for the force of friction. It's doing something like this. That's a big arrow. Anyways, you get the idea. Here is our force of friction. Okay, let's note that this is going to be a clockwise